A real revolution is starting. But it's not happening in some high-tech lab or inside a supercomputer. Nope, it's starting quietly from the resin vat of a 3D printer. This is a revolution built not on silicon, but on pure, perfect geometry. And it might just change everything we think we know, from how we measure the world to how we teach machines to actually think.
And I mean that, literally. What if you could print an object that isn't just a close enough approximation, but is the physical embodiment of a mathematical truth? An object where its very existence is a perfect, tangible theorem you can touch and feel. Well, that's the incredible idea we're diving into today.
So here's the game plan. First, we'll look at how these perfect objects get created from nothing but pure code. Then, we'll see how they're forging a new gold standard for measurement itself. From there, we'll jump into how this whole geometric approach is teaching AI to reason. And finally, we're going to ask the big one. Could geometry be the native language of the entire universe? All right, so how do you even begin to take a totally abstract mathematical idea and give it a real physical form? Well, it doesn't start with complicated 3D scans or messy models. It starts with the elegant, beautiful simplicity of foundational mathematics. It all boils down to something that looks ridiculously simple, like this single line of Python code defining the golden ratio, phi. And what's absolutely astonishing is that from fundamental constants just like this one, you can generate the precise, perfect coordinates for these incredibly complex shapes. We're talking dodecahedra, icosahedra, the whole gang. It's pure mathematics just expressed as code. And here's the key to making sure that perfection isn't lost along the way. These objects are defined using something called a boundary representation, or BREP. You should think of it as the ultimate digital blueprint. See, unlike a mesh of triangles or a bunch of pixels, a BREP file doesn't just approximate the shape. It describes the exact continuous mathematical surfaces. So what you print isn't a good copy, it's a provably perfect replica of the mathematical ideal. Okay, so we can print mathematically perfect objects. Cool. But why is that such a game changer? Well, because it lets us create an entirely new system for measurement and verification, a physical library of truth. This quote just nails the scale of this idea, doesn't it? By systematically printing these mathematically defined solids, we're creating a physical library of standards. These aren't just useful little calibration jigs. They are the standard. Each object is a self-contained, provably correct artifact that can be used to verify, well, pretty much anything, from high-tech optical sensors to the accuracy of other manufacturing machines. You have to understand, this is a massive shift in thinking. For centuries, our standards have been centralized. Think of the standard kilogram that used to be kept in a vault in France. Everything relied on these long, complicated traceability chains to make sure your scale was accurate. This new way, it's completely decentralized. Anyone, anywhere on the planet with a good enough printer can create a perfect standard because its correctness comes from the math baked right into it, not from some central authority telling you it's correct. All right, now let's talk about how this same geometric foundation is shaking up the world of artificial intelligence. And believe me, it has some profound implications for teaching machines not just to recognize patterns, but to actually reason. Today's large language models they're amazing, but they have an Achilles heel, formal reasoning. Just look at this chart. When you give an LLM a math problem, its accuracy takes a nosedive as the problem gets harder. They're great with the simple stuff, but that complex, multi-step logic really trips them up. And the reason for that is actually brilliantly simple. LLMs don't really get math in a formal, logical sense. They are absolute masters of pattern matching. They've seen billions of examples of text, and they can predict the next most likely word with scary accuracy. But that's not the same thing as understanding the basic axioms of geometry or logic. So what's the solution? Well, we need to teach AI to think in the language of geometry. And that's exactly what geometric deep learning, or GDL, does. Instead of just throwing pixels or words at a model, it teaches the model the fundamental geometric principles that govern the data, things like symmetry, invariance, and structure. So for example, a GDL model wouldn't just see this building as a flat collection of pixels. No, it would see it as a graph of nodes and edges representing the deep geometric relationships, the windows, the arches, the structural supports. It understands the blueprint, the bones of the object. And because it understands that blueprint, it can recognize the fundamental symmetries and patterns. It sees the repeating arches of the Colosseum not just as a pretty visual texture, but as a fundamental, repeating geometric instruction. It's learning the rules of the game, not just memorizing a million past games.
And this doesn't just stop with rigid objects. A GDL model can understand the intrinsic geometry of things that bend, twist, and deform, like the complex protein structures folding up inside our own bodies. I mean, this just blows the doors open for incredible applications in biology, medicine, material science, you name it. And we have absolute stunning proof that this works. Google DeepMind's Alpha Geometry 2, a system built on these very neurosymbolic principles, recently hit a gold medal performance at the International Mathematical Olympiad. Think about that. It's solving problems that stump some of the brightest human minds on the planet by combining the pattern-spotting intuition of a neural net with the hardcore logic of a symbolic reasoning engine. It's happening.
And that brings us to our final and maybe most mind-bending section. If geometry is the key to unlocking machine intelligence, what if it's also the key to understanding the fabric of reality itself? Well, you don't have to look any further than the future of cybersecurity. The next generation of encryption, the stuff that's being designed to be unbreakable even by quantum computers, it's built on geometry. Lattice-based cryptography works because it's insanely difficult to find one specific secret point hidden inside a complex, high-dimensional, crystal-like structure. The security of our future data literally rests on a geometric problem.
And this is where it all comes together. This idea is so profound. The physics will echo the number theory. Just let that sink in for a second. What if the physical properties of an object, how it actually behaves in the real world, are a direct consequence of the abstract mathematical laws that define its very shape? Okay, let's break that down. The coordinates of these 3D printed shapes, the ones that come from constants like the golden ratio, they belong to a very special mathematical field. And this field has unique properties tied to prime numbers. Now, and here's the crazy part. Imagine you build one of these shapes out of some advanced material, like a superconductor or a photonic chip. Its physical performance, how efficient it is, how stable it is, will literally be governed by those deep number theoretic laws. By embedding math into matter, the physical laws and the mathematical theorems become two sides of the exact same coin. So we end on this question. We've gone from a simple 3D print to a new standard for truth, to a new architecture for AI, and all the way to a new foundation for physics. It really suggests that geometry isn't just a tool we use to describe the universe, it might be its fundamental operating system. And we are just now learning how to write the code. What happens next? Honestly, that's anyone's guess.